Welcome back to the second lab session of Module A. In assignment 3, we all found that Hartree-Fock method is unable to correctly predict the molecular orbital energy level diagram of O2. In this module, we'll see how a post-Hartree-Fock method, that is multi-configurational self-consistent field, will tackle that problem. But before that, what I'll suggest you should go through the theory lectures of present module, which is about post-Hartree-Fock method. This is how the molecular orbital energy level diagram of O2 will look like. The highest energy two unpaired electrons are present in degenerate pi star 2p molecular orbitals. Below that, pi 2p molecular orbitals are also degenerate. Then below that, we have sigma 2p molecular orbital. But do we get this particular feature using Hartree-Fock calculation? If we look into the output file generated from a Hartree-Fock calculation, in this case, if I scroll downward, that's the summary of the input file, where in this case, Hartree-Fock calculation has been performed, optimization calculation, with the split basis set, Popel split basis set, double zeta for the valence shell orbitals. This is the input which we have to provide for obtaining molecular orbital, for visualizing molecular orbitals. That's the specification regarding the molecule O2, where the spin multiplicity is 3 because there are two unpaired electrons in this case. So if I scroll downward, this job was terminated normally. That's the message. ORCA terminated normally. Let's scroll upward. Now, one of the issue with Hartree-Fock calculation is in case of open shell system having unpaired electrons, we get two different set of energy level. One for spin up and another one for spin down. And for example, the 1s alpha spin molecular orbital and the 1s beta spin molecular orbital, they do not have same energy. For example, in this case, you can see that spin up for this 1s with one particular spin has energy minus 20.76 in atomic unit, that is Hartree. And if I scroll downward with the same spatial molecular orbital, that is 0 number, that is actually molecular orbital number 1 corresponding to 1s. For spin down, the energy is minus 20.71. So minus 20.71 Hartree for spin down and minus 20.74 Hartree for spin up. So that's one of the issue with Hartree-Fock. Second, in this case, we have taken O2. So O2 has how many electrons? Total 16 electrons. Out of 16 electrons, 2 of them are unpaired. Those 2 are present in antibonding pi star molecular orbital. So 7 molecular orbitals are completely filled. So 7 to 2, 14 electrons, that will comprise 14 electrons. And the other 2 are present in pi star molecular orbital. Means out of 16, 9 will have a particular spin and other 7 will have another opposite spin. So in this case, the spin up total 9 electrons. You can see that if you count this 0 to 8. So 0 to s spin orbitals, that is total 9 spin orbitals, they have one particular spin. So look at that occupancy 1, 1, 1. That's it. Till there. Now it is 0. So 9 electrons have spin up. And if I scroll downward, spin down, you'll find 7. 0 to 6. That is occupancy 1. So 9 electrons spin up, 7 electrons spin down. That means the 2 unpaired electrons correspond to spin up. So the last 2 unpaired electrons, you can see that are present in molecular orbital number, because the numbering starts from 0, so it is 7 and 8, but actually it is 8th and 9th molecular orbital. So these 2 are actually pi star molecular orbitals. And you can see that energy, the energy is same. That means there is these two molecular orbitals are degenerate, which are pi star molecular orbital. This energy is in Hartree. If you want to convert that into electron volt, you have to multiply this with 27.2. So if you multiply this with 27.2, you get the energy in electron volt. These two are degenerate, but below that, these two, they are no more degenerate. Actually, the pi 2p molecular orbital, which is below pi star 2p molecular orbital, should be degenerate, but that's not the case what we are getting from our Hartree-Fock calculus. If you visualize this in Avogadro, so let's upload this output file in Avogadro. If I go to Avogadro, let me discard this. And let me open that output file. So go to open and then navigate to the desired folder. That's the output file. So let's upload this. See, yes. Now Avogadro has some issues because they have no way to assign a particular molecular orbital as half-filled molecular orbital, that is singly occupied molecular orbital. So what they are saying, so these two, that's 7th number and 8th number, which has energy minus 0.54 atomic unit. If you multiply this with 27.2, you'll get the value minus 14.8 electron volt. So one of them they are assigning LUMO, actually it is singly occupied molecular orbital, and another one they are assigning HOMO. So that's the two molecular orbitals. If I select this, that's it. The shape is correctly, that is pi star, shape of a typical pi star molecular orbital. This one also has pi star molecular orbital. Rotate this. So these two, they are degenerate. So correctly, for means Hartree-Fock at least is giving correct picture of the molecular orbital. For the highest two molecular orbital, that is pi star molecular orbital, but below that, these two molecular orbital, that is shape is correct, that is dumbbell form, that is the shape of pi 2p molecular orbital. This one is also pi 2p molecular orbital. So these two shapes are correctly predicted by Hartree-Fock method, but not the energy. They are no more degenerate. This one, this is sigma 2p. The shape is correct, but not the energy level. So the obvious question is how to obtain the correct electronic structure of O2. You'll get the answer in the theory section of the present module, where there is detailed discussion on various post-Hartree-Fock methods. In the lecture 2 of module 8, there is discussion on multi-configuration self-consistent field method. And a special case of this particular method is complete active space self-consistent field method. You'll find detail about that in the ORCA manual. So if you scroll downward in the content section, you'll find the topic, I think in section 8, complete active space self-consistent field method. So if we click on this, we'll be directed to this particular page. Look at the first line, what they say, there are several situations where a complete active space self-consistent field treatment is a good idea. They have listed out the situations, and then they say, in all these cases, the single determinant Hartree-Fock methods fails badly. The first one, you can see that it talks about nearly degenerate configurations. We know that in O2, we have degenerate orbitals. Let's see if this particular method is able to give the correct electronic structure or not. But making an input file for this particular calculus is a bit tricky. You should have an idea about the partially occupied active orbitals, the one which contain active electrons. So in case of O2, the last two electrons which are present in pi star molecular orbital can be treated as an active electron, and those orbitals can be treated as partially occupied active orbitals. So to make the input file, take the help of ORCA input library. If you go to the ORCA input library, there is a section called Complete Active Space Self-Consistent Field Calculations. If I click on this, you'll go to this particular page. So you can take the help of this particular input category. So in the keyword, you have to apply the methodology, the basis set, and then you have to provide information regarding how many active electrons are there and how many active orbitals. So in case of O2, we'll take this value to 2 unpaired electrons, and those are present in the molecular orbitals pi star. So we'll take this value also as 2, but spin multiplicity will take this value as 3. So we'll copy this, copy from this point to this point, and then paste that into the Avogadro input section there. So if you visit Avogadro, so I've already created that O2 molecule. The comment I've made electronic structure of O2 using complete active space self-consistent field method. We are doing a geometry optimization calculation. Now regarding basis set, let's have a discussion on the basis sets available in the drop-down menu of Avogadro. These are def2 basis sets. Let's go to the ORCA manual again. And if I scroll downward, there is a section called Standard Basis Set Library. So if I click on this, all the basis sets which can be used in ORCA are listed here. 321G, that's the simplest Popel type split basis set. We already had discussion on this. Then Slater type orbitals obtained from 3 Gaussian, but they are no more of any practical use. Only for demonstration they are used. Practically, most of the time we'll be using Popel split basis sets like 631G or 6311, that's a triple zeta for the valence shell orbitals. But note, these Popel type basis sets, these split basis sets are only for lighter elements. Look at this, 631G is from hydrogen to zinc till atomic number 30. What about heavy metals? Again, along with this, we can combine this particular basis functions with polarization function as well as diffuse function. By mistake, I made a wrong statement regarding this star in the last video. 1 star is equivalent to the D functions for period 2 elements other than hydrogen, and 2 stars means you are adding polarization functions also for the hydrogen atom. So in place of dp you can have 2 stars, and in place of 1d you can have 1 star. The diffuse function represented by plus. These are Popel basis sets. They are only useful for lighter elements. For heavy elements, you have to take into consideration effective core potentials. There is a discussion on effective core potential in the theory section of module 7. But in Avogadro, we can also use another category of basis set, that is from the Karlsruhe group, that is def2 basis sets. These def2 SVP stands for double zeta basis set. Then we have triple zeta, then quadruple zeta basis set along with the polarization functions. So these are the ones which are listed in the drop-down menu of Avogadro. The plus point of these Karlsruhe group basis sets are you don't need to get a separate basis set for heavy element with the effective core potentials. The effective core potentials are automatically loaded in these type of basis sets. So they are very useful. So from now onward, we'll use these basis sets for our calculation. Go to Avogadro, click no. Now we have to provide information regarding number of active electrons and number of active orbitals. For that, take the help of ORCA input library, copy it again, and then paste just below the line which contains important information regarding the calculus which has to perform. That's the important keywords. And then paste it here. Now change the value. The number of electrons, let's make it 2. That is active electrons. Number of active orbitals, let's make it again 2. Sorry. And then number of, that is multiplicity equal to 3. So I think we are done with this. This is the section which is for printing the basis set and the molecular orbitals detail. This we got it again from the ORCA input library, from the visualization and printing section. So this is from where we have copied it. And now I think we are ready for submission. So click on the generate button. Give a proper name to the input file. Let's make it post Hartree-Fock. Click on the save. And now take the help of your command line to submit the job. Let's see if I have got that file or not. Yes, that's there. So the command ORCA, name of the input file, channel 2, the name of the output file, change the extension name to .out, click. So it's running. So hopefully within few seconds, we'll get our job completed. So done. Now let's analyze the output file. So let's open the output file in Notepad. And now if I scroll downward, it says we have taken the basis set, def2 basis set. That's the summary of the input file. So we have performed complete active subspace self-consistent field calculation, number of electrons, active electrons 2, number of orbitals, active orbitals 2, multiplicity 3. That's the section for printing detailed information regarding basis set and molecular orbitals. And that's the geometry specifications. Spin multiplicity 3, Cartesian coordinates for the O2 molecule. And now, if you go to the end of the file, the message which we want to see, ORCA terminated normally. I scroll upward. Now, do we have separate levels for the spin up and spin down? The answer is no. So that problem is solved. We are only getting information regarding the spatial molecular orbitals. Now you can see that the first one, which is labeled as 0, it's the orbitals corresponding to sigma 1s, molecular orbital corresponding to sigma 1s, which are formed by the linear combination of 1s of one oxygen and 1s of another oxygen. And here you can see that maximum value, because this molecular orbital is formed by all these atomic orbitals, but the maximum contribution is from 1s of one oxygen and the 1s of another oxygen. Rest has contribution nearly 0. So this is minus 0.7. This is also minus 0.7. That means same sign. So it will correspond to a positive type combination. The second one, again, maximum contribution from 1s of this oxygen and 1s of this oxygen. But look at the sign. The value, in this case, it is 0.7. Here it is minus 0.7. So opposite sign means that will correspond to an anti-bonding molecular orbital. But these two are for the core electrons. So we are not bothered about sigma 1s and sigma 1s star. So normally in molecular orbital energy diagram, we start from sigma 2s. So sigma 2s, this is the column for sigma 2s. Now you can see that the maximum contribution in the creation of this particular molecular orbital is from 2s of this oxygen, that is 0.41, and again 0.41. So the maximum contribution to this particular molecular orbital, which is sigma 2s, is from the 2s of each atomic orbital. Sorry, 2s of each atoms. This another one, the next is sigma 2s star, and that is from the linear combination of these atomic orbitals. All the atomic orbitals are involved, but the maximum contribution is from the 2s of one oxygen and then the 2s of another oxygen. You can see that the sign, this sign is 0.4, the value is 0.45, and here the value is minus 0.45. So opposite sign means this particular molecular orbital will correspond to an anti-bonding molecular orbital, that's a sigma 2s. After that, almost all these molecular orbitals are formed by the maximum contribution is from the p orbitals. The last two electrons, we can see that total oxygen has 16 electrons. So out of those 16, 14s are paired. So in the first 7 molecular orbitals, you can see that numbering from leveling from 0 to 6, completely occupied, each having 2 electrons. Whereas these two, labeled 7th and 8th, actually that is molecular orbital number 8th and 9th, they are singly occupied. And the energy, look at this value, they are degenerate. So the pi star molecular orbitals containing unpaired electrons are degenerate. Below that, the pi 2p molecular orbitals, this and this, look at the energy, 0.73597, 0.73597. That means these two are also degenerate. So it means we are getting the correct energy level diagram using this complete active space self-consistent field method. Below that, it is the orbital corresponding to sigma 2p. Now let's plot this in Avogadro. So take the help of Avogadro, open that .out file, so navigate to that desired folder, so O2, post Hartree-Fock, and then let's open this particular output file and let's analyze that. So you can see that the last two unpaired electrons are present in these two molecular orbitals. Actually, they are singly occupied molecular orbital. One of them, Avogadro is labeling as LUMO and HOMO. This is not the correct way to write that, but that's the last two molecular orbitals. If I select this, you can see that yes, we are getting the correct picture for pi star molecular orbital. This is another pi star molecular orbital to rate this. Again, double dumbbell shape. So correctly, we are getting the shape as well as the energy, the degenerate. Below that, this is sigma 2p. Yes, that's a sigma 2p, the dumbbell shape. Sorry, this is pi 2p. This is pi 2p, and this is also pi 2p. So the two pi 2p molecular orbitals are doubly degenerate. Below that, we have sigma 2p molecular orbital. So we are getting the correct picture. Below that, we have sigma 2s star. This is sigma 2s star. So I think the visualization in Avogadro starts from sigma 2s star, then sigma 2pz, then the two degenerate pi molecular orbitals, and then the two degenerate pi star molecular orbitals. It means with the help of this post-Hartree-Fock method, that is multi-configurational self-consistent field method, we are able to get the correct electronic structure of O2.